Okay, we'll go ahead and get started. Thank you everyone so much for joining us today. Our next press briefing right now is the Solar Orbiter Science Begins. I'm Lauren LaPuma from the AGU Media Relations Office, and I'll be moderating today. So just a few housekeeping things to start off with. The slides from this presentation will be available online in the Fall Meeting Media Center, and the link is right there on the slide, and my colleague Liza will also put it in the chat box for you. This event will also be recorded, and the recording will be posted to AGU's YouTube channel later this afternoon, and it will be available to the public in perpetuity. After we do our panelists will give some presentations, and then we'll have time for Q&A. And then afterwards, if anyone would like to stick around and have some more chat and discussion with the panelists, we will open up an informal discussion room via Zoom. And my colleague Liza will post the link to that event, to that meeting in the chat box as well. And if you have any problems connecting or any questions at any time, you can email us at news@agu.org. And so with that, I will turn it over to our panelists. So our panelists today are Daniel Mueller, Teresa Nieves, Tim Horbury, and Frederick O'Shea. So guys, take it away.
Thank you, Lauren, and good morning, good afternoon, and good evening to everyone joining us today. Solar Orbiter is on its way to explore the Sun and heliosphere, and we'll give you an update today on what the mission has been up to since launch in early 2020. And as Lauren said, I'm here with Teresa Nieves, the NASA project scientist, Tim Horbury, the chair of our Insitu working group, and Frederick O'Shea, the chair of our remote sensing working group. Next slide, please. Solar Orbiter is a mission of international collaboration between the European Space Agency and NASA, building on the successful missions we've done together in the past, like Ulysses and SOHO. And Solar Orbiter is tackling a large overarching science question in heliophysics, namely how the sun creates and controls the huge plasma bubble blown into the interstellar medium by the solar wind, and why solar activity changes with time. And how will Solar Orbiter do this? We will observe the sun in many different ways, all the way from the surface out into the solar wind. We will measure the solar wind as it streams past the spacecraft. We measure the complete plasma state, electric and magnetic field, and energetic particles coming from the sun, all the way into 0.28 astronomical units, which is closer than the perihelion of our innermost planet Mercury. And we complement these measurements in situ, where we feel the solar wind, by telescopic observations with 6 remote sensing telescopes, where we observe the entire sun in a variety of wavelengths, all the way from the visible to X-rays. And in particular, we are after the uncharted polar regions of the sun that we believe hold the keys to unraveling the mystery of the sun's magnetic activity cycle. And a specialty of Solar Orbiter is to do the simultaneous imaging and spectroscopic observations to not just provide pictures, but actually physics information about what's going on the solar surface and how that then translates into dynamics in the solar wind. And we have 2 wide field coronagraphs that image also the space around the sun, and one of which, the Solar High heliospheric imager, even captures the space that NASA's Parker Solar Probe mission is flying through. And we published a series of papers in a special issue of Astronomy and Astrophysics in September, and this QR code will take you to that journal issue. And so the focus of Solar Orbiter is really to get close to the sun and out of the ecliptic plane, and that's why we focus really on the perihelia and the high latitude observations. Next slide, please. Mission milestones so far. We launched on a picture-perfect evening in February 2020 in what feels like centuries ago. It was at a time when many people still thought that Corona was just a beer. We had a perfect launch on the NASA-provided Atlas rocket, and Shortly after launch, the COVID-19 pandemic struck, and that required all instrument teams and also part of the flight control team to carry out the commissioning and early operation activities from their homes. That was a first. It wasn't supposed to happen like that. People didn't know whether it could be done, but they rose to the challenge, and I'm extremely proud of all the teams that pulled together in that way and made sure that we could commission the spacecraft on time and successfully and be ready for first observations in mid-June, when we passed the sun at half an astronomical unit. And a month later, we held our first media event to show the first light images and particle and field data. And that was quite successful. And that enabled us to move forward with the first public data release in September, which is also, I would say, unprecedented and very impressive, and big kudos to the instrument teams that made this happen on this time scale. So that early in the mission to make the data available right away to the scientific community. A few weeks from now, we'll have the first of many gravity assist maneuvers at Venus that we use to tweak our trajectory. And next November, we'll start our nominal mission. And then in the March of 2020, we have the first close flyby of the sun at roughly a third of the Sun-Earth distance. Next slide, please. So in the first light media event, we showed our first engineering type images. And we were surprised by the high quality of these data that were not really science data yet. And still, we could see unprecedented detail of the sun in the corona. And there were features that hadn't been spotted before that were dubbed campfires that seem like tiny versions of the solar flares that had been observed for decades. And we believe that they might be or related to what is called nanoflares, that are small bursty releases of energy that happen all the time on the sun, as postulated by Eugene Parker many years ago, and could explain what makes the corona millions of degrees hot. Next slide, please. On this slide, I'll try to walk you through the 10-year journey of Solar Orbiter in roughly half a minute. So if you click one more time, the animation should start. Okay, so after our first Venus flyby, we have another one, and then an Earth flyby in November of next year. And as you can see, our orbit gets successively more tilted with respect to the plane where the planets fly, and also gets closer to the sun as we move into the nominal mission. And in the extended phase of the mission, starting in 2026, 2027, the orbit gets really inclined to a degree that we can see the sun's polar regions as we've never seen them before. So that will be very exciting. And now I'll hand it over to Teresa, who will tell you a little more how our 10 instruments on board will be working together.
Thank you, Daniel. Hi, everyone. Yes, Solar Orbiter has 10 instruments that will allow us to observe the turbulent surface of the sun, and then also to study how this sun turbulence change and will take place later in the solar wind. You will hear more details about that from Frederic Aucher and Tim Horbury. And they will tell you about the amount of instruments, the kind of instrument, and also the location of these instruments. Some of them, as you see here in the architecture of our spacecraft, are located in the boom, in the long boom, to keep them isolated from the electronics of the body of the spacecraft, to allow them to measure the sensitive electromagnetic fields in the solar wind. Next slide, please. One of the key elements in solar wind is that we need to combine the measurements, the observations that we have from the sun, and the measurements that we will take later in the solar wind. The success of Solar Orbiter is based, therefore, in the teamwork. The different instrument teams will work together in order to accomplish the goals of this mission. For instance, we have here one example. By means the spectroscopy will allow us to observe, to image the spectral lines of heavy ions in the surface of the sun. We measure oxygen, carbon, iron, for instance, and then later with Insitu Instruments, we will also take measurements of these heavy ions. This is very important for solar orbiters. We are going to be able to connect what is happening in the sun, what is happening in the solar wind, and to better understand our sun and the atmosphere of our sun, that is where we live, right? Now we are going to learn more about the remote sensing from Frederic Hauscher. I will hand over him. Thank you.
Okay, thank you, Teresa. So I'm going now to talk a little bit more in detail about the remote sensing science. So the payload has been introduced already in the previous talks by Daniel and Teresa. So these instruments, these remote sensing instruments, are telescopes. So the Insitu Instruments will measure, as their name say, what happens directly in the vicinity of the spacecraft. Here we are looking at the sun and its heliosphere. We make images and spectra to learn about the sun. We embark 6 of these instruments, which can sound like a lot, but it's actually needed if we want to make sure that we will be able to record everything that there is to see in these new places that we're going to. Can you go to the next slide, please? We're going indeed to new places with Orbiter. As Daniel said, we are first going to go close to the sun. Closest approach is going to be about 42 million kilometers. That sounds like a lot, but it's actually very close to the sun for telescopes. When you are an instrument that's staring directly at the sun, that poses very tough challenges technically, but we've been successful in overcoming these challenges and building very, very beautiful and very performant instruments. And if you press yes, so that's an enlargement that's showing the type of zoom that orbiter will be able to make on the solar surface. That's one of the best images that we have so far to date, but that's still far from what we will get when we will be at closest approach. So here we have a big question mark on these regions. So next, and next again. The next new place where we're going to is above the poles. And here I put in a pretty fuzzy image, and that's normal. That's only a simulation. Here, really, we've never been there. So we don't really know what we're going to find there when we will be at 30, 35 degrees of solar latitude, because for now, from Earth, we have only a very grazing view of the polar regions. And as Daniel said, we know that these regions are very important to understand some of the most important problems in solar physics. So this is very exciting because it's a lot of discovery space. We're going closer than ever, and we're going higher than ever. And we really don't want to miss anything there. So next slide, please. So when I said in just a few seconds ago that we don't know what the sun will look like when we will be there, I lied a little bit, because we actually had a very good glimpse of what we will see already back in March. We were very lucky that even during the commissioning phase, so the period during which the instruments are tested, we got close to the sun, down to about 0.5 astronomical units, so a half of the distance to the sun. And we were happily not surprised, but we were happy to find that our instruments were functioning perfectly, and we were able to record already a very, very sharp sequence of the aspect of the solar corona. And that's actually sharper than what we had before from Earth. And in the movie that you see here, which is a sequence of only 5 minutes on the sun, we see a myriad events, tiny events. And these are, as Daniel said, we think are similar to what we knew before on the sun at larger scales. So we think these things are tiny eruptions, which are by themselves really nothing. They don't carry a lot of energy, but it seems that they are there all the time and everywhere. And if we have enough of these, then we are able to solve one of the long-standing problems in solar physics, which is to understand why the solar atmosphere is at about 1 million degrees or so, while the surface is much cooler. And next slide, please. So after that very first excitement, when we saw that the instruments were indeed delivering very, very sharp images, that we're zooming in here on one of these tiny flares. So on the top left, you have an image taken by EUI, and on the bottom left, you have a comparison with, that's the same event, but observed by the SDO spacecraft that's orbiting the Earth. So you see that already we have this dramatic improvement in the resolution. These blobs are now separated into tiny substructures. But beyond the simple imaging, Orbiter is also capable of making spectra of these events. And that's what you have on the top right. So the SPICE instrument is able to analyze the light emitted by these events. It's able to measure the physical properties of the plasma that composes these events. It's able to measure, for example, the temperature, the density, and the velocity that's of these events. And we detected in some of these very strong Doppler shifts, so very strong velocities away and towards us, that are the signature of very interesting activity. And so we don't know yet, because we don't have yet simultaneous observations with EUI and SPICE. We don't know yet if these velocities in these tiny events observed by SPICE are related to what EUI sees, but we think they are, and that's we're really eagerly waiting for the observations that we will be taking in February to check that indeed we are looking at the same thing and that we will be able to analyze and understand these events. Next slide, please. So Orbiter embarks, as I said, this very comprehensive suite of telescopes to be able to make this comprehensive set of measurements. We are still fine-tuning, I would say, the parameters, the acquisition parameters of all the telescopes. We are not yet in the nominal mission phase, but already we see we have a good, we know that our instruments are working really well. You have examples here of the granulation. That's this top left image, the granulation at the solar surface. This gray disk that you see may seem like nothing, but it's actually the first magnetogram. So the black and white dots that you see are upwards and downwards magnetic fields. And it's the first time we take this kind of magnetogram away from the Sun-Earth line. And that's quite important, because by combining these measurements with what we do from Earth, then we will able to learn a lot more about the magnetism of our star. And then I talked already about SPICE. So SPICE is able to measure velocities and temperatures and densities. And then finally, we have the ability also to measure what happens in the X-rays, which tells us about the acceleration of particles in solar eruptions, and helps us make the connection with what happens then in situ. Next slide, please. And then when we zoom out from the sun, we have two other instruments that make images at large angles. So on the left, you have an image from what's called the Coronagraph. It's an instrument in which you have actually a mask that blocks the direct sunlight to avoid to be blinded by the direct light from the solar disk. And that instrument reveals the faint corona around the sun, so the sun's atmosphere. And if you zoom out once more, then you have what we call the heliospheric imager, which observes a large fraction of the sky on the side of orbiter. And in this image, you see the Milky Way in the background, stars. You see a comet, actually, on the top right of the image. And also, you see that that halo that's across the image is actually the interplanetary dust, and on top of that, we will see ejections, coronal mass ejections propagating from the sun out to the heliosphere, and the ejections that will eventually go and pass solar orbiter, and that will be analyzed in situ by the Insitu suite of instruments. And with that, I hand over to Tim.
Thanks, Frederick. Hi, everyone. I'm Tim Horbury. So I'm chair of the Insitu working group. So I'll talk a little bit about the Insitu instruments and the early science that we're doing. And also I'll talk about the connection. So as Daniel mentioned at the beginning, Solar Orbiter is really about understanding what happens on the sun and how that influences interplanetary space. And to do that, we need to know the connection between the two. So I'll talk about our early work on that as well. So as we heard from Teresa, there are 4 Insitu instruments. So they are measuring the conditions locally in space around the spacecraft, the magnetic and electric fields, the particles coming from the sun, the solar wind, and also very fast moving energetic particles that are accelerated at shocks or at solar flares, for example. And we're also measuring radio waves that are generated near the sun and in interplanetary space that give us an idea about conditions as well. So it's quite a comprehensive package. As Frederick says, these instruments complement the remote sensing telescopes, so we can do that joined up science that we need to do. Okay, if we go on to the next slide, please. So one of the great advantages of the Insitu instruments is we're lucky enough that we're basically able to operate all the time around the orbit. So that means we've got lots of data over a long period of time. We've already basically been around the sun once. So the plot on the left-hand side of here gives you an example of some of the data that we've got from the energetic particle instrument, EPD, which is measuring these fast-moving particles. So that's a plot of basically of our inner solar system. So the sun is the yellow dot there, and the orbit of Solar Orbiter is plotted on. We went anti-clockwise around the sun. You can see the dates there. And what's plotted on here is basically the fluxes, the amount of energetic particles that are electrons on the inside of this plot and ions on the outside. And really what you can take from this is to start with, as we launched sort of near the left-hand side of the plot, the sun's been very quiet. We've been in a really deep solar minimum, very low solar activity for the last couple of years. So there really wasn't a lot going on at all. So that's one of the sort of stories of Orbiter. We've started in this very quiet sun conditions, but the sun is just beginning to wake up now to go through its next solar cycle. And as you can see, gradually, so there's sort of red bursts appearing. They're energetic bursts of particles that are coming from the sun. So Solar Orbiter is gradually seeing this activity building. And these Insitu instruments that we're flying on Solar Orbiter, they're the most modern instruments. They're very sensitive, they're very capable, and also we have very good data rates. So we have very good time resolution on the data as well. And those things combined with being close to the sun is letting EPD measure very fine scale structure in those particles and how that's controlled by the magnetic field in ways that we haven't been able to before. So lots of new science very early on. Another example of the kind of fortuitous science we can do with Solar Orbiter is Comet Atlas. So we launched in February, as Daniel mentioned. And not long after that, it was realized that actually a comet discovered by the Comet Detecting System Atlas was actually going to fly between the sun, between the sun and Solar Orbiter, so that Solar Orbiter might well fly through the wake of the comet. So other spacecraft have flown through the wakes of comets before, but not very often and not this close to the sun. So we were pretty excited. But actually, as you can see from this picture taken by the Hubble Space Telescope, before Solar Orbiter got a chance to get there, the comet actually disintegrated. And you can see the various fragments here in this image. So we really weren't sure what we were going to see. Nobody's flown through the tail of a comet that's fallen apart before. And actually, we saw something very different to what we've seen before. So very weak signatures, nothing like a big, strong comet tail signature we've seen before. But we've got evidence of dust there and some waves that are being generated by the interaction of the cometary particles with the solar wind. So this is new science for us. We've never seen something like this before. And so we're working away at those data to try and understand this really unique interaction that we've never seen before. Okay, if you go on to the next slide, please. Here's another example of some great fortuitous science. So this was done really early on in the mission in April. So this is a time when we were still really in commissioning and not all the instruments were on yet. The plot on the left-hand side is looking down on the solar system. So the sun's in the middle of that plot. If we do next, please, then you can see key labels there. So the sun in the middle, we're off on the right-hand side of the Earth, obviously. And solar orbiter was about 20% of the way between the Earth and the sun, but pretty well upstream. So the solar wind coming from the sun passed solar orbiter before it arrived at the Earth. And there's a spacecraft at the bottom of that plot there called Stereo. That's a NASA spacecraft. So you can see just how many spacecraft there are around the inner solar system these days. It's fantastic. And Stereo has an instrument on it like Solar High that Frederick mentioned, that can actually image the solar wind. And what's shown in the middle here is an image from Stereo showing a large discrete object traveling from the sun on the left towards the right. And that's a coronal mass ejection. That's a transient eruption of material from the sun. And that was headed straight at the Earth. This is quite a well-formed example. It's a really nice image of one there from Stereo. That crossed over solar orbiter about 20 hours before it arrived at the Earth. And so we can measure it at solar orbiter. We can measure the magnetic fields associated with it, for example. And we also see it at spacecraft near the Earth when it arrives. So we can see how that CME evolves as it travels away from the sun in a way we've really never been able to do before. And also we can use those measurements to try and constrain models of those structures, which is what's shown on the right. And that's really a plot of what that large scale structure would look like. And you can see the positions of the various planets there. And we can compare that with those stereo remote sensing observations as well to try and understand the structures of these things better. It's interesting, actually, this is an event that really couldn't be seen from telescopes near the Earth. So we didn't get good warning of that from the Earth-based telescopes, so-called stealth CME. So this is very interesting from, for example, for looking at space weather. When this arrived, it actually produced a significant magnetic storm at the Earth. And so these are the kind of events we really want to be able to predict better. And these solar orbiter measurements really help us understand these events in more detail. Okay, if we go on to the next slide, please. So as Daniel mentioned at the beginning, solar orbiter is about understanding the connection between what happens on the sun and what happens in interplanetary space. So to do that, solar orbiter, we go close to the sun to measure the young solar wind. We carry telescopes to look at the source regions on the sun where the solar wind is being made that then arrives at solar orbiter. But quite where that solar wind comes from is quite complicated, and it involves some complicated magnetic field mapping. What's shown on the left-hand side here is an image of the sun taken from a telescope near the Earth called the Solar Dynamics Observatory, a NASA spacecraft, in ultraviolet light. And this was during this time in June that Frederick mentioned when we had this remote sensing checkout window. This is when EUI saw those campfires, for example. And from Earth's perspective, solar orbiter was off to the right-hand side. And we can do that mapping and work out where on the sun that solar wind really should have originated. And that's what's shown there by that red ellipse on the right-hand side. But you can see it's right around the side. It's really hard to image that very well. If you look on the right-hand image, though, this is taken with EUI. So we're looking full on the sun, and you can see that ellipse is really clearly, that the source region of that ellipse we can see really clearly. And we can see that actually that solar wind was coming from the equatorward edge of that dark polar region, which is called a coronal hole. And these are magnetically open regions where the solar wind can stream into space. So we can map quite accurately where the solar wind comes from. So this is great. And that means that we can start looking at how properties on the sun can affect the solar wind. And if we go to the next slide, please, this will actually be a movie. So if we can start the movie, then here we go. So this is a movie of that same data. And I hope you can see there's a green cross up towards the north. That's actually the real-time mapped foot point of where the solar wind originated that ultimately arrived at solar orbiter. And you can see how that moves around the edge of the coronal hole as the sun rotates underneath solar orbiter, and we end up mapping to slightly different places. So this is really early preliminary work. There's a lot of work to do. This certainly isn't finalized. It isn't completely fixed, but it gives you an idea about the kind of thing we can do, because using these movies, we can see how the sun is actually changing. And for example, with SPICE and the other remote sensing instruments, the properties of the solar wind source region, and then compare that with how things are changing in interplanetary space at solar orbiter itself. So it's early days, but I think this really shows the promise of solar orbiter as a spacecraft. And there's an enormous amount we're going to be able to do in the years to come. So it's really exciting early days. And with that, I'll pass you back to Daniel.
Thank you very much, Tim. I think everyone can tell how excited we are as scientists to have this mission in orbit and operational now. Just wanted to give you a one-slide summary and wrap up our presentations by saying that what we've tried to show you in the last 25 minutes is to highlight that Solar Orbiter has already now, after less than a year in orbit, provided us with new and unprecedented views of the sun and heliosphere. We are really measuring all the way from our home star out into the solar wind. And in a few years' time, we'll produce the first ever images of the sun's unknown polar region. So that will be another first a few years from now. As Tim mentioned already, we now have a fleet of solar and heliospheric missions in orbit. So that is just a fantastic opportunity to study the sun and the solar wind from different perspectives and understand better what's going on. And this is complemented by new telescopes on the ground, like the recently inaugurated 4-meter Inui Solar Telescope on Hawaii. Together, we believe we can really do a lot of new and joint science to take solar and heliospheric physics and our understanding of the solar system to a new level. And in terms of the timeline, we are just now starting to produce the first scientific results. We'll publish them early next year. We'll have the first Venus flyby a few weeks from now. And then in 11 months, we'll swing by Earth for one last time before we then dive right into the inner heliosphere to get close to the sun in March of 2022. And with that, I would like to close. Thank you for listening. And of course, we are happy to answer any questions you might have.
Wonderful. Thank you so much, panelists. So now reporters will open it up for questions. Please, if you have a question, type it into the Q&A box that's separate from the chat box. It says Q&A. Type it in there. Please remember to state your full name and affiliation, and my colleague, Liza Lester, will pose it to the panel on your behalf. Do we have any questions to start off with, Liza?
Yes, we do. This question is for Tim from Leo Enright on Irish TV. He says, stealth CMEs? I thought they were always, oh my God, events. Could really dangerous CME hide itself as stealth?
Yeah, that's right. So it could, that's right. So stealth really means that it's a CME that is released from the sun and arrives at the Earth, and we don't really see it coming from Earth-based telescopes. So we have telescopes that are making those artificial eclipses, looking for those events coming. And sometimes when they're coming at the Earth, you can sort of see them as a so-called halo around the sun. They sort of gradually expand out as they come and then come over the top of the Earth. So some of them just aren't visible like that, and this was one of them. And so they don't have to be enormously effective events when they arrive, but certainly they could be. So one of the things we'd like to do is understand those stealth events in more detail. What I would say as well, it's interesting because we have some spacecraft upstream of the Earth, the so-called first Lagrangian point. That gives us about 45 minutes notice of measuring the magnetic fields and the particles in the solar wind. So that's the kind of notice we get now of a big event coming, whether it's stealth or not. Solar Orbiter at the time was far enough upstream that actually gave us about 20 hours notice of that. So in the future, it would be really nice to be able to put a spacecraft there, for example, with a solar sail or something that would give us much more warning about these kind of events in future. So this event is actually a really nice example for Solar Orbiter about how we could use this as a sort of demonstration about what we could do with that kind of capability in future.
From Megan Bartels from space.com, she asked, Tim touched on the solar minimum and the beginnings of solar cycle 25. Could you, and perhaps Frederick as well for the remote, speak more about any evidence of the solar cycle change you've seen so far, what you hope to see in the current months, and why the timing of the mission's beginning with the cycle switch is intriguing?
Sure. Shall I say something from the in situ side, and maybe if Frederick, you want to say something from the remote sensing side? I think so at the moment the sun's field is, well, it's changing even now, but let's say when we launched in February, the sun's magnetic field was relatively simple, kind of like a dipole. Solar minimum, it's most like just like a bar magnet pointing kind of north-south, in the sense that as a result, the sort of magnetic equator was very close to the sun's main equator. And so the structure, it was very much like a northern hemisphere and a southern hemisphere. And the spacecraft at the moment, we're traveling actually at very low latitude. So our inclination is only about 7 degrees to the solar equator. But even that was enough for us to flip in and out through that boundary. So we've actually been skimming over the top of that boundary repeatedly. So this is it's a very thin boundary. It's only a few degrees across. So at the moment, we're getting some really interesting measurements, and as a result, there were kind of very few energetic particles. Even now, that is beginning to tilt up. So it gradually warps up, and it looks more like the seam in a tennis ball, and that'll gradually happen over the next sort of year or so. So it's actually a really good time for us. We managed to launch in this very minimum conditions, which we've obviously never seen close in before. And then gradually that will evolve over the next year or two. So we'll be able to essentially map out a whole solar cycle about how the sun's magnetic field evolves and how it affects things in interplanetary space. And for example, we're going to see more energetic particle events and so on. So I think we timed it exactly right. I'd love to say we planned it that way. We clearly didn't, but I think it's gone exactly right in terms of transitioning from that minimum up towards the maximum. And I guess, Frederick, you want to say something from the remote sensing side?
Yeah, I totally agree. I mean, it's the exact best time for us also. With catching the end of the minimum, which is good because that also gives us a point of comparison with the previous minima. That helps us also to compare our observations with what we knew before, and it's easier to compare the observations of different instruments when the sun is at its in minimum of activity. Now we're going to see in the next month and years the rise of the activity. This is very exciting because we will see more of these large events, which will look just gorgeous with our telescopes. But also from a scientific point of view, also that means that we will, as Tim said, cover a large fraction of a cycle, if not a whole solar cycle, including periods during which we will be able to measure the magnetic field configuration from above the poles, which has never been done before, and which is very important to finally maybe be able to understand exactly how the solar cycle works. Right now, you can ask different modelers. They will give you very different predictions for what the sun will be or will look like in 5 to 10 years. We basically don't know really well how to do that. We know the basic ingredients, but we don't know how to put them together really well so that we have predictive power. And Orbiton definitely will bring key elements to the final answer.
For Frederick, Leo Enright from Irish TV asked, the magnetogram seems to show a donut feature around the South Pole. Is that an artifact or a real feature?
So that's, if I think you're referring to what I think you do, well, that's, I think a residual from indeed an artifact from the processing. These data, the data that you see is still very preliminary. The instruments are still being tested, optimized. And this instrument has only a few engineering sequences, so to speak. So we still have a lot of optimization to do. I think the important thing with that image was that it shows that first the instrument works. There's still some tuning, some fine tuning to do, but again it shows the solar magnetic field from a different viewpoint. And by combining that with what we measure from Earth, we are basically able to do what we call stereoscopy, so we can reconstruct the three-dimensional structure of the magnetic field much better than what we do now with only a single viewpoint.
For Tim from Lisa Grossman at Science News, how can the solar wind be coming from only one point? And can you give any more details about the things you're learning about the solar wind's origin from these observations?
Yeah, sorry, I probably wasn't very clear in the way I said it, Lisa. Sorry. So the solar wind fills all of interplanetary space. So it goes out in every direction. But if you're in a particular point in space, where on the sun did the particles that go past you at this moment in time come from? So to do that, we have to essentially the wind flows roughly straight away from the sun, radially away, far from the sun. But as you get closer, it's affected by the magnetic field, and it goes through the sun's complicated magnetic field structure. And so we have to do some mathematical mapping of, basically we map that when we measure some solar wind at solar orbiter, we sort of map it back at a speed, and then we run it through that complicated magnetic field structure, and it plonks down to a particular point on the sun. So you sort of go backwards in time and say, if I measure it today at solar orbiter, then it turned out, last Tuesday at 3:30 in the afternoon, it left the sun at that point there. And then we can look at the EUI image from that point in time and say that's where it came from. And then we can do it the other way. If it was on an EUI movie at a particular place, then when, almost everywhere on that movie, the wind will not hit solar orbiter. There'll only be one place on any given picture where it will hit solar orbiter. And that is about identifying that spot and how it moves in time. And actually, we do see some of the effects of that straight away in the early work. If you remember the edge of that coronal hole, it's not symmetric around the pole. It's got sort of fingers. It's got like little ripples in it. And the mapping says that we're sort of jumping across these fingers. And actually, it looks like as we jump across those fingers, we're actually seeing signatures in the solar wind, like little compressions and rarefactions as the wind speeds up and slows down as we go across those. So it's really early days, I would emphasize, but it looks like we're already seeing that really fine scale structure in the solar wind and being able to link it to particular structures in those coronal holes, which would just be fantastic. But there's a lot still to do, but it looks like we're already being able to see that fine scale structure.
And Lisa follows up with, for the panel, can you talk a bit more about how Solar Orbiter and the Parker Solar Probe can work together and give a new view of the sun?
Yeah, I don't know. I'll say something briefly. I guess maybe other people want to as well. I think, and actually there's Parker and the Solar Orbiter. There are other spacecraft too, like Bepi Colombo, which is an ESA Japanese spacecraft, which is cruising around the inner solar system as well. So we've got this fleet of spacecraft in the inner solar system. And we can do things like, and Parker goes very close to the sun. There was a time in September when Parker went close to the sun and Solar Orbiter was actually further away from the sun, but in the same direction. So we've measured the solar wind and the magnetic fields that went past Parker that then arrived later at Solar Orbiter. So we can see how it evolves with distance away from the sun. So there's lots of processes that we want to see how they, as the solar wind matures, as it goes away, how those things change. Those kind of things are great. I guess with the remote sensing observations, like Frederick might want to talk about how the, Parker would actually be in the field of view of some of those telescopes at times. So again, we can do that kind of source linking. Frederick, I don't know if you want to say something.
Yeah, that's right. I mean, that's, you showed, Tim, one of these nice images in which you see large coronal mass ejection that propagates through the field of view of the heliospheric imager. And depending on the orbital configuration, at times we will see Parker in our fields of view, which means that we will see Parker being hit by one of these big eruptions. So in these configurations, we have an image of what's going on, and then in other configurations, Parker will basically see in situ, sample the plasma in situ before orbiter, so we will be able to track the history of the plasma and see what happens to that same blob of plasma with the two different probes. So that there are many different types of configurations that are interesting for the two probes to work together.
For Daniel from Megan Bartels at space.com, are there any plans for observations during the Venus flyby? And if so, what would that look like?
Thank you, Megan. That's an excellent question. And I should say two things. I mean, A, we are always looking for bonus opportunities to do science. So yes, we will be doing observations when we approach Venus. The second thing to say is that Solar Orbiter is, of course, a mission not designed specifically to take Venus observations. So one of our constraints is that we always need to point our heat shield towards the sun. So that cannot be changed. And the telescopes are all looking through that heat shields in the solar direction. So that's why we will not be able to image Venus. But what we will be able to do is have the Insitu instruments, or at least a significant fraction of them, be operating. So, for example, the magnetometer, for which Tim is the principal investigator, the radiant plasma wave instrument, and some of the energetic particle detectors will be on. And we will be very interesting to see what they will measure. our first Venus flybys will appear at the closest approach of about 8,000 to 9,000 kilometers, so relatively far away from the planet. But the future one will go down to roughly 500 kilometers. So we'll really be looking out for new and interesting things. We can't really say yet what they will be.
Yeah, I would just say we're looking for at those kind of distances. It's looking at how Venus interacts with the solar wind that's flowing past it is going to be, I guess, the key thing we're going to be looking at. And Venus doesn't have a magnetic field, so the Earth has a magnetic field, and so the solar wind interaction is really with the magnetic field, whereas Venus doesn't have one, so it's a very different interaction. So I think that's the kind of thing we're going to, at least from my perspective, we're going to be looking at. Yeah, so yeah, my instrument's going to be on, and we're I think Daniel's right. We don't really know what we're going to see, but we'll look forward to seeing what we can.
And for Daniel from Leo Enright, a very similar question. Do you have plans to look for phosphine gas in the clouds of Venus? And is that, he notes that there have been some discussion about whether you can see the wavelengths necessary to do that.
Right, that's another good question. And as both of you know, I mean, there's been an intense discussion about the recently reported results that I don't want to go into really. I'm also not a chemist, but from what I have been told by people who do know the atmosphere of Venus quite well, is that this phosphine, should it exist, will really be present at really low altitudes, so around up to 120 kilometers. So that is not the regime and the distance to Venus where we will fly through. So we will not be able to detect it in situ. So, as I said earlier, we will be sun pointed at all times. So I fear that in this particular aspect of Venus science, we might not be able to shed new light on this aspect.
All right, we've reached the end of the questions in my queue. My cat's name is Beezus, for those who have asked. Sorry for his cameos. Are there any other questions? Last call.
Okay, well, it looks like that's it. That's all the open questions that we have. So thank you again for everyone for joining us. Thank you to our panelists. So now if anyone wants to stick around and just have any additional discussion with the panelists, one-on-one or in a small group, you can join us in this post briefing discussion room, and the link to that is in the chat box here. It's just a regular old Zoom meeting. The passcode is AGU press, all lowercase. So you can go ahead and click on that link and switch over, and we'll close out this briefing shortly. Thank you again to all of our panelists for sharing your work.